So we're going to just practice integrating and differentiating some of these power series. And again, these power series are really easy to integrate and differentiate because these are just polynomial powers, and we can just apply our power rule when we differentiate, and we can apply our power rule when we integrate. There is something that you do have to be a little bit careful of is when we differentiate, we may end up, or even integrate, we have to watch out where we're going to start from, just because sometimes the terms don't match. Sometimes we're dividing by 0, things like that. We have run into some issues like that. So we just have to be a little bit careful when we're doing that. So the power series, it says the power series representing f of x is differentiable on the interval of convergence. Then the derivatives and integrals we must have derivatives and integrals on that same interval. And so the radius of convergence is going to be the same. If we have this radius of convergence for the original function, the derivative and the integral should have the same radius. Okay, not necessarily the same endpoints, but the same radius. So we can differentiate and integrate this power series to get a derivative and integral of this function. Okay, so I'm just going to do it up here. So if I differentiate, okay, 1 over 1 minus x, okay, the derivative is going to be equal to negative 1 over 1 minus x squared. And then the chain rule, we have that positive, and the integral of 1 over 1 minus x dx is going to be log 1 minus x plus c, and then chain rule, I have to have that extra minus in there. Okay, so those are my derivatives and integrals, so I can actually just do this right on the power series. So I can differentiate my power series. Okay, so the series that represents that is going to be x to the power n. This is just a power series from n equals 0 to n equals infinity. Okay, so the derivative of this, when we differentiate, is going to look like this. It's going to be n x to the power n minus 1. Okay, n minus 1. That's our power rule for our derivative. And then we're going to start at n equals, in this case we have to start at n equals 1. Just because we're going to end up with a negative power if we don't do that. So we want to make sure that the power is going to be the right power on there. Okay, so there we go. There's a derivative. Okay, so there's the derivative for that particular function, and this power series here then represents this function. So we can actually say this. Okay, 1 over 1 minus x squared is equivalent to this infinite series. Okay, so we can use this series to approximate values on that 1 minus x squared function. So we can do the same thing here. We can integrate this series. So we're going to take the integral of this series from n equals 0 to infinity of x to the power n. Okay, and then we're going to end up with this new series. Okay, so it's going to be x to the n plus 1 all over n plus 1. Okay, and this is going to go from 0 to infinity. There's my new series. So what we can say is then this function, plus c. So what we can say then is that this function, negative log of 1 minus x plus c is equal to this series. Okay, and so we can make this equivalent. We can also solve, in this case, if we give an initial condition, we can actually solve for c. So if I plug it in, y equals 0 of negative log of 1 minus 0 plus c, we can actually solve for c. C just works out to be 0 in this case. Okay, so plus 0 plus c, and then we can make that c equal to 0.